Once we understand the rules of probability, we need to look at how events can be represented and how probability can be calculated from different types of representation. In general, probabilities are based on either a result of an experiment or what we can theoretically expect to happen. So an experiment would be something like tossing a coin and then counting how many tossing a coin 10 times and then counting how many heads and tails you get. So that the results you get are based on an experiment. If we are rolling a dice, then theoretically you can expect to get a 1 out of 6 times. The probability of getting a 2 would be 1 out of 6 and so on. So that would be theoretical and not based on experiment. Now, once you get results from different theoretical or experimental probability, you can represent them in different ways. So they're represented and calculated either from given information, so they tell you the different probabilities or the different ways events can happen. It can be represented in a sample space, so they list out all the possible ways things could happen. They could be given in tables, like normal frequency tables, for example. They might be given in two-way tables, Venn diagrams, tree diagrams. So these are all different representations of information, and based on these representations, you can calculate probability. We will focus on two-way tables, Venn diagrams, and tree diagrams because probabilities from sample space table and given information are quite basic. So again, on experimental and theoretical, we talked about this just now. So the probability of, for example, as mentioned here, tossing a coin. So you might experiment it and see what you get, but theoretically, it's always a 50-50 chance. So for the experimental probability, the number of times the event occurs over the number of trials. For the probability event, the number of favorable outcomes over the possible number of outcomes. From probability, so this is a nice kind of mind map just to show you how different things are calculated. If the event is to roll a 6 on a die, if I'm going for theoretical probability, then my sample space would be just 1, 2, 3, 4, 5, 6. And they're all equally likely outcomes. So the possibility of each one happening is 1 over 6. And if I'm looking at the probability of rolling a 6 on a die, that will be the number of ways the 6 shows up, which is 1, over the number of things I have in my sample space, which is 6. And I can also calculate the probability of the complement, which is 1 minus probability of A. In the experimental probability, let's say I roll the dice 200 times and I get 37 times, which means the relative frequency is 37 over 200. So that would be the relative frequency, or what we call also the probability of this experimental event. Now, we have something called expected events. We'll look at this a bit more later. But if I have the theoretical probability and in reality I'm rolling 200 times, then I can combine these two things, so the theory and the practical together, to find the expected number of sixes I could possibly get. So if I'm rolling my dice 200 times and I know that I will theoretically get a 6 1 out of 6 times, and multiplying them together, so the total times the probability will give me 33 1/3, which means I am expected to get that many sixes in 200 rolls. The idea is that the more you do the more trials you have in your experiment, the closer your results are to the theoretical probability. So this is a fact, and this is an equation that we will frequently see throughout as we even dive into probability distribution. So keep this in mind. As we said, relative frequency, if you do the experiment over and over, then we can calculate the relative frequency, and that would be almost the probability. So relative frequency would be the frequency of the event divided by the number of times you tried the event. So let's practice it with this one. So we have a spinner here, and it was spun 100 times, and we have the results in the table shown. So the number of times 1 was scored, 2 was scored, 3, and so on. And you can find the estimate probability by finding the relative frequency. So we take for the number 1, I will take 10 divided by 100. For the number 2, I'll take 14 divided by 100, and so on. So I can find the relative frequency. And then I can answer things like, is the spinner biased or not? Because this is based on an experiment. Theoretically, all of them have a possibility of showing up 1 out of 6 times. But based on my experiment, this is what I'm getting. So once you find the relative frequency, try and answer this question if it's biased or not. So we can see the probabilities here, and we can suggest that the spinner is biased because if you look at the frequency of 3, it's much higher, and the frequency of 1, 5, and 6 are much lower. So it would be biased. Otherwise, you would expect them all to have almost the same numbers. And again, the more times you do the experiment, the more accurate your estimates of the probability would be. So maybe repeating it 200, 300 times would make it a bit more accurate. Expected frequency, as we talked about before, you can estimate how often you'd expect something to happen if you carry out an experiment n times. So the expected probability is calculated by taking the probability multiplied by the number of trials. Again, you will see this calculation show up again when we do probability distribution. So have a look at this question, try it out. And then question 2 is asking, estimate the number of times they'll win in 180 separate attempts. So have a go at this question. So first we calculate the probability of winning, and that would be 2 out of 6, which is 1 over 3, because there are 2 ways of getting a 5. Or so you either get a 5 or a 6, which are 2 possible options. So then when we do the expected value, if they're playing 180 games, so we need to take the probability of winning times the number of trials, so 1 over 3 times 180, which means we can expect that out of 180 separate attempts, they will win 60 times. So back to the representation of probability, we can represent probability in what we call a sample space. So we list out all the possible ways things can happen. So this would be about heads and tails, for example. And then from here, I can organize what I'm getting in a two-way table, for example, in a tree diagram, an event diagram. So these are all different ways of representing probability. And based on each representation, we calculate probability slightly differently, but you should get the same answer if you're using equivalent data. First, we'll talk about two-way tables, not in too much detail, but we'll just have a look at how two-way tables can be used. So two-way tables are used when you have two categorical variables. So if we look at this question, so a teacher was asked for the mode of transport they use to travel in school and the gender. So based on this, these are actual just numbers, not probabilities. I can answer, for example, the probability that someone would travel with a car. So I know in total, there are 37 male and 30 female without specifying the gender. So just car basically is 67. And then in total, I have 105 people that I survey. So the probability of someone traveling by car is 67 out of 100. So I'm looking at this. But if I'm looking for the probability of female and car, then I'm looking at specifically just this 30 here. So my probability would be 30 over 105 directly. So no need to worry about intersections and so on. You can directly take the information from there. If we're looking at females in total, for example, then I'll add the female row and I'll get 48, for example. If we're looking at fully female, then I'll get 48 out of 105. So the total of the table, that would be the total, your denominator, and then the values that you need, you can spot from the table, either a complete row or a complete column, or an individual cell based on what they're looking at. Questions on probability can build up later once you do conditional probability and so on. you can then apply those type of questions to two-way tables. So for example, once you do conditional probability, you can ask something like, what's the probability of that someone rides a bike given that they're female? So then you'd do a different calculation. So this is an example you can have a go on your own. So again, we are just taking random probabilities and from the table here. And you need to be careful about things like or and. So for example, during the peak season, so calculate the probability that someone is booking during the peak season or they're picking a family room. So we're looking at or two separate things. So peak season would be this, all of this, and then so this would be peak season or a family. But remember what we talked about when you have an or, so you're adding those two things, you need to subtract the intersection because you don't want to double count it. So you have to subtract the 98 in here. If I'm looking for instead in part II, I'm looking for a single room in off-peak season, then it's specifically those two conditions together. So single room in off-peak season will just be 148. So you just need to be careful about the wording of the question in these two-way table. So Venn diagrams are a typical representation. You can get two Venn diagrams, three Venn diagrams. Make sure you know how to fill up a Venn diagram. That's the most thing students struggle with. Once you know how to fill it up, then answering the probability is easy. Also know how to shade in or recognize the area that they're looking for in a Venn diagram. Again, that can be done through a practice from the previous lesson. So just to practice how to fill this up, so in a class of 24 boys, you have 16 that play football, 11 play baseball. If 2 play neither, how many play both games? So you don't know the intersection, but you know that all of football is 16 and all of baseball is 11, which means when I say 16, I'm also including the intersection. So both of these add up to 16 and both of these add up to 11. So you need a mathematical way to find the intersection. So if I know that 2 play neither, it means the total of football and baseball is adding up to 22. So those two should add up to 22. Now, my technique that I like to tell students is to always, if you don't know the intersection, always represent it with an X. Always start with the inside, the very inside, and then work your way out in a Venn diagram. So if this is my inside, if I know what it is, then substitute it with a number. If you don't know, then just write an X. And then start going outwards. For football, it's now going to be 16 minus X. And for baseball, it's going to be 11 minus X. And now what do I know about all these three values is that if I add them up, they should add up to 22. And then using that, you can find the intersection. So in this case, it's going to be 5. Once I have 5, I can then answer some probability questions. So for example, if they ask me calculate the probability of football union baseball, which means someone either plays football or baseball. So remember, this is calculated either directly by taking these numbers, 11, 5, and 6 directly. I can see what that will be. So that will be 22 out of 24. Or I can use the rules for the addition rule, which is probability of F plus the probability of B minus the probability of F intersect B. And that will be, the probability of F would be 16 over 24 minus 11, sorry, plus 11 over 24. And then minus the intersection, which is 5 over 24, because we're double counting the intersection, remember that. And that will give you, sorry, that will give you 22 over 24. So the same answer, either way. If I'm looking at football union B complement, so either interpret what that means. So I'm looking for football or not baseball. So just to word that specifically. So I'm looking for either football. So translate, you know what it means, or not baseball. And if you've practiced shading the regions, you can easily recognize the numbers that you need. So I'm either looking at football, so I'm going to highlight the football numbers I need, and then not baseball. So I'm looking at the baseball circle and I'm highlighting everything outside of that. So that would be the 11 and the 2. And because I'm looking at union, then I'm going to take into consideration everything I shaded, which is the 11, 5, and 2. So the answer will be adding those two up all together. So the 11, the 5, and the 2, all over 24, and that would be 18 out of 24. You can also do it mathematically again if you want to. So the probability, sorry, using the addition rule if you want to, probability of F plus the probability of B complement minus the probability of F intersect with B complement. So the probability of football would be 16 over 24. The probability of not baseball would be the complement. So 1 minus 11 over 24. So we get, remember, complement of events. So you get 13 over 24. And then you need to subtract the intersection of football and baseball, and not baseball, which if you see, this is where I shaded twice, which is 11. So I need to take away 11 out of 24. And if you calculate this probability, you will see that it will give you the same answer. So there are different ways to answer these probability questions, but using probability rules and axioms correctly. And then in here, no need to do much. If you notice, the complement is on the outside. This is football or baseball, and then the complement of that. We already did football or baseball, which is 22 over 24, which means the complement of that would be 1 minus 22 over 24, which is just 22. Or you can understand what they're asking. So not football or baseball. So if you're not football or baseball, then you're playing neither. That would be 2 over 24. Now for 3 Venn diagrams, again, try this question on your own or read. The slides are already detailed. If I reveal the answers, I do also have a separate video on this specific question that you can watch. But the idea remains the same on how to fill up these 3-way Venn diagrams or 2-way Venn diagrams. Always start with the center and then start building in the intersection. So if you have this information, if you know the intersections, fill them up, but always start from the very, very center. Be careful if a question says, for example, so you have 29 in total that you need to know. If you know that 15 biology, it means all of biology, all of this circle adds up to 15. So the number here, 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 and here add up to 15. So you need to recognize that. So 15 take chemistry, 18 takes physics. And then they give you specific information like 10 take biology and chemistry. So you know that this time, this and this will add up to 10. So just need to be careful about where the intersections are. And then they tell you 5 take chemistry and physics. So chemistry and physics would be these two. So these two would be 5. And then 7 take biology and physics and so on. So we don't have information about who takes all 3. Let me just fill up the last one. So 7 take biology and physics. We don't have information about all 3, but we know, so we represent it with an X. And then we build up to the next intersection. So if I know that 10 take biology, so all of this has to add up to 10. It means that this will be 10 minus X. And if I know all of this is 7, then I know this small section will be 7 minus X and then 5 minus X. So using this technique is really helpful. Start with the center, build to your next intersection and then next. And then I know all of biology is 15. So it's going to be 15 minus all of these values. So minus 10 minus x, minus 7 minus x. So all of these that are part of the biology circle have to be subtracted from 15. Be careful with the algebra. So minus open bracket, write out the values. Minus open bracket, write the values. You will have a lot of algebraic terms in there, but then simplifying them will help you find the x value that you need. It will also help you find all the other values. So this is what it would look like. So you can pause and read through this so that it basically explains what I said. And you can notice the minus and the brackets are there accordingly. Once I have that, I know that all of these have to add up to 29 because 29 take one or more. So I don't have anyone that takes none of the subjects. So all of these have to add up to 29. I know the algebra might seem long, but things will cancel out easily. Once you write it out, be careful how you write it out, how you expand your brackets. You'll eventually get, you'll eventually be able to simplify these. So notice how chemistry eventually simplified to x, biology simplified to x minus 2. This is 6 plus x. So I know that all of these will be adding up to 29. And then I can easily solve for x, which will give me 3. So once I know it's 3, I can then fill up the rest of the values. And you can double check your answers. So for example, check that biology and chemistry add up to 10, check that chemistry and physics add up to 5, and then physics and biology add up to 7, and so on. Just check everything. So how many students take all 3 subjects? X would be equal to 3. But how would it look like as a probability question? So I would say a student selected at random, what is the probability that the student takes all 3 subjects? So you are looking for the probability of B intersect C intersect P, and that would be 3 out of 29. But in order to get here, you need to make sure you fill up the Venn diagram correctly. And again, later on, when we do questions like conditional probability and so on, we'll see more complicated ways of dealing with these Venn diagrams. Next would be a tree diagram with and without replacement. So if we look at tree diagrams, if I ask you to complete this, so you've probably seen this before. So remember that probabilities have to add up to 1. So if I have the probability of not waking up as being 0.6, then the probability of probability of waking up late is 0.6, then probability of waking up late would be 0.4. Sorry, not waking up late. Then probability of being late to work 0.7, which means not late to work would be 0.3. So it's just the complement. And that's what's nice about tree diagrams. You always get these complement events in there if you're dealing with like 2 branches. So a probability tree diagram is a good visual representation. It's when you have different events happening. You don't need to memorize the names of the branches, but it's good to know what's happening. So at the end of each branch, you get the outcome, the possible outcome. So for example, here, the end of here would represent waking up late and being late to work. And the end of this branch represents waking up late and not being late to work. So at the end of each branch represents an outcome. And you can list out the probability of each branch. And then we can do different calculations like conditional probabilities and independent events. We'll see that later. So how do I calculate the probability in tree diagrams? So each branch represents an option that could possibly happen. So this represents one option, this is another option, and so on. To calculate the probability of one outcome, you multiply the probabilities that are going on each route, if you think of them as routes or paths. So if I'm looking at this path, then the probability of this path would be 0.4 times 0.7. If my outcome is showing up from different possible options, then I need to calculate all of them and add them together. For example, if I'm only looking for the probability of being late to work, only late to work, then late to work shows up here. It also shows up here. So if it shows up here, it means I have to come this route. Okay. So if I'm coming on this route, So late to work shows up on two possible routes. So because of that, I need to calculate the probability of the first one and the second one, and then I'll add them together. So I'll calculate the probability of waking up late and being late to work, which is 0.28. And then I'll calculate the probability of not waking up late but still being late to work. So that would be 0.12. And then, so being late to work, it could happen for two possible options, either the first one or the second one. So because I'm using the word or, notice, or remember is an addition. So I'm either I wake up late and be late to work, or I do not wake up late and be late to work. So I have to add those two options up. So 0.28 plus 0.12. That will give me the total possible the probability of being late to work. So that's just being late to work, regardless of what happens in the beginning. Do I wake up late or do I not wake up late? So this is what this explains. The probability of each outcome is calculated by multiplying the probability of each branch leading to that outcome. The probability of an event can happen from different outcomes. In this case, add up the probability calculated from each outcome together to give the probability of that event. So we've already calculated this. So being late to work, we've calculated this as 0.4 times 0.7, which is 0.28. Because we're looking for and, remember, so he wakes up late and is late to work. So that's what we're looking at. And then we are looking for does not wake up late and is late to work. So remember that and refers to a multiplication in math. So that can help you understand when to multiply, when to add. And I either wake up late or I do not wake up late. So I have two possible options. So I get 0.4 out of that. In tree diagrams, we need to consider repeated events happening. So the same events just repeating, but we need to take into consideration something called replacement. Does the second event repeating impact the first event? Are they independent or not? We'll dive into this deeper a bit later. But this is usually very clear about, the questions are usually very clear about whether the repeated event is a replacement or not replacement. So just an example here. If you look at the top example, so this would be a repeated event with replacement. So for example, you're picking a disk from a bag, you have 7 blue disks and 3 red disks, and you're choosing a random disk, you're noting the color, and then you're returning it to the bag and then picking another option. So this is important because replacing it back does not impact the total probability. So if I'm picking blue and my first pick, I have a 7 out of 10 possible ways. If I'm picking red, it's 3 out of 10. Now, because I've returned it, when I try to pick a second time, I still have 7 out of 10 blue and I still have 3 out of 10 red. And if you notice, we tend to write the outcomes at the end here. So blue, 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 red, red, blue, red, red. And then I can calculate the probability of blue, blue by multiplying, blue, red by multiplying, and so on. But when we come to without replacement, so you pick the desk and without returning it to the bag, and then you're picking a second time. In this case, you have to, if you notice, the denominator decreases because you have one less item to pick from. And then the numerator decreases based on where you are in the calculation. So if my first pick was blue, in my second pick, I have one less blue, but my red did not change because in that first path, I did not pick red. So we have, these would remain the same. The 3 would still remain the same, if you notice, but then the blue is decreasing. But in general, you'll notice that the denominator is always decreasing as you go to the next pick because you have one less in general to pick from. So as I'm going in this path, the blue is decreasing, the red stays the same. As I'm starting in this path, the blue stays the same, but the red decreases. And when you calculate the probabilities, notice how different they are with the replacement probabilities. So they are quite different. So you just need to be careful with questions that are with the replacements and without replacements. For without replacements, for example, you can try out this question if you want to. We have 3 cards are drawn from a deck of playing cards. Each card is not replaced. Find the probability of obtaining 3 picture cards or 2 picture cards. So first represented on a tree diagram. This will be a bit of a big tree diagram because you have 3 events. And you can see the highlighted colors showing how the probabilities have changed. So if I pick picture, 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 then it starts with 12, 11, and then 10. And you can see the denominator decreasing as we go along. And at the end, I just listed out all the probabilities because this will help me answer the question. So for part A, I need 3 picture cards. So I'm looking for P repeated 3 times, which is the first option. So I'll multiply these. If I'm looking at 2 picture cards, then I'm just looking for 2 P values, and they didn't specify the order, so the order does not matter. So I'm looking at this option, and that's it. Those would be the 2 possible options. So I have this, and then I have a third option here. And then you can calculate the probability of the green paths and add them together. That's it for the different representations. You can have a go at these questions, just practicing each of the different representations and making sure you understand how to find the probabilities of each one.